These are the video notes for some more on 4.3. So just take the notes and I'll check them when you come into class tomorrow right away. And so we've been talking about how integrating gives us the area under the curve, and when we have what we call a definite integral, which means it has what we call limits of integration, it's really just giving you the parameters under which you find the area under the curve. So if the A was maybe 2 and the B was 5, it just means find the area under the curve between 2 and 5. And it's actually under the curve and between the x-axis. So you go under the curve until you hit the x-axis. So kind of keep that in mind. And that's given by the function f of x dx. And really loosely, this right here represents the height of all those little rectangles, an infinite amount, and this represents the base of all the little rectangles. And when we make the base length, which is really our change in x or our dx, when we make that incredibly small and have it approach 0, it's really a kind of a limit question, and we make the number of rectangles out to infinity, the integration actually does give us the area under the curve. And we call this a definite integral. Whereas when we first started this chapter, we had ones without any limits on them, and that's called an indefinite integral. And there is a difference. The definite integral, yes, it has the numbers on that integration symbol, but that gives us a numerical answer for the area between the curve and the x-axis. Whereas this means find the antiderivative of f of x. And so they are actually quite different. We're going to tie them in together in the next section in 4.4. And that tie-in where we can use that definite integral to find the area under the curve, not just when it's geometric like it was yesterday, where we graphed the curve and it ended up being, a line like this, and we said, oh, well, we can get the area under there by doing the area of a triangle. That's true, but what do I do when it's curved? And that tie-in is coming in the next section, and it's one of the huge calculus claim to fame, and it gets the title of the fundamental theorem of calculus. The FTC is sometimes what we'll call that. And there's two fundamental theorems of calculus, but the first one will be coming at you in the next section, 4.4. And before we do that, before we figure out how do we get the area under a curve without a calculator when it doesn't make a geometric figure, and I want to have you understand where we're going. So just briefly, we know that, again, when I graph under the curve, and maybe I go from 0 maybe out to 4. And if it was this one, between the curve and the x-axis, I have a trapezoid. So when I integrate from 0 to 4, the area under that line and the x-axis, I can get a numerical answer for the exact area because that's a trapezoid, and I can do 1/2 the height times the sum of the bases. We have also talked about, and you don't need to write this part in your notes, we have also dealt with these curves like this, maybe going from A to B, where we did rectangular approximations. We did right rectangles where we went up and hit on the right, etc., and we did left ones, but those were approximations for the area because there was little gaps that were left in and left out, and that was an approximation. Now what we are going to be doing after we learn how to kind of work with these properties a little bit more is we are going to be able to find exactly what the area is without geometry, all right, and without a calculator. And that's our big task in Chapter 4. But first of all, we're going to have some properties today, and that'll be basically it. The first one, when I integrate from A to B, It's exactly the same as if I change the limits of integration and go from B to A, then I need to throw a negative correction out front. And let me explain why that is. And you'll get really used to this one because we use it quite a bit. But the reason is because what happens is when I go the other direction, dx becomes negative. So if I want them to be equal, I have to self-correct with a negative out front. So what that means is, going from 2 to 5, f of x dx, I could go from 5 back to 2, but that's going to give me a negative change in x. To go from 5 to 2, I have to be negative. So I correct that with a negative correction out front, and then I'll get the exact same value. The next one, number 2, when I integrate and my limits of integration are identical from 3 to 3, 4 to 4, a to a, what that means is there is no change in the x-axis along the x-axis, which means there really is no area, so the answer is 0. What that means is if you integrate from 3 to 3 of any function, dx is going to be 0, and when you multiply by 0, you get 0. The next one up is when you have a constant in here, you are allowed to bring it out front. That's just going to become second nature to you. That's an easy one. So constants come out front. Number 4 is intuitive, that when I do the integral of a sum, I get the sum of the integrals. So instead of doing them as one, it is perfectly legal for me to split them up into 2. And really what this means geometrically is instead of doing one big area, I can split it into 2 and do them separately. All right, the next one. When I integrate from A to B, and again, this one is pretty self-explanatory also. I'll go give you a little picture of what this one says. If I integrate from A to B, so I'm going to find the area under the curve. If I take any value in between A and B, it's very legal for me to split it up into 2 integrals where I go from A to C. So let's do that. And I find that area first. Then I go from C to B, and I add them up. That's a C. I kind of like to think of, if you were to take and wipe that off, whoops, you'd be going from A to B. But really geometrically, you can just add up the 2 as long as C is something between A and B, obviously. The last one we don't use a whole lot, but it actually is kind of important, and that is it doesn't matter what your variable of integration is, whether you call it t, x, u, w, that's equal. So the variable's name doesn't really matter. It never really has in our work. So let's go take a look down here. Let's see if I can scroll this. It says there's a benefit to writing all of them out as we did above, but just in case you missed it, I put them all on the next page explained in more detail. So on the top of this next page is everything I just told you. And then we're going to practice using the properties. So what I'd like to do first is I missed a page back here. Sorry, go back a page in your notes and let's just kind of make sure you understand how to read all of this notation first off. So what I've got going here is for part A, again, for the notation, I am being asked to find the area from 0 to 2 of f of x dx. It's important to know that anytime you fall below the x-axis, your integral will be negative. You might say, how can area be negative? It actually isn't. The integral gives us what's called the signed area. So this is considered negative, 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 positive. And the reason is because this f of x, or this height of every rectangle, will be negative. So it's going to balance out to be a negative integral. So integration gives us the signed area. So let's go from 0 to 2. From 0 to 2, along the x-axis, I need to find the area between the curve and the x-axis. So it's really just that little wedge right there. That's what this is asking me to do. So that is a circle of radius 2, and it's a fourth. So I go 1/4 pi r squared. But it's below the x-axis, so I do need to put a negative there because the integral gives me a signed area, S-I-G-N-E-D, for the sign of it. And that just gives me pi. Let's go look at B. From B, I'm supposed to go from 2 to 6. So I'm going to go back up here. From 2 to 6 of the area. Well, again, this is a triangle. Again, the only ones we know how to do right now are ones where it makes a triangle, a rectangle, a circle, or a trapezoid. Otherwise, all we know how to do is approximate. Until the next section, the best we can do is approximate unless this makes a geometric figure. Because for a triangle, I can do a half of the base times the height. And on this one, the base is 4 and the height is 2. And so my area is 4, and it's above the x-axis, so that integral would be a positive 4. For letter C, I'm going from negative 4 to 2, which means I'm going to go from negative 4 all the way to 2, which means I need to do this triangle and then half of a circle, and it's all negative. So the triangle right here is 1/2 of the base times the height, but it's negative because it's under the x-axis. The circle is 1/2 of pi r squared, but again, it's negative because it's under the x-axis. The triangle I just did, it was 4 and it's above the x-axis. So what I would have here is a negative 1, and then I would have minus, and I'd have a half of 4, which would be 2 pi, and then plus 4. So the best way to write this would be 3 minus 2 pi. And letter D would be done similarly, so I'm not going to do that one. Letter E is worth looking at because when I put those absolute value signs around the f of x, really what that does is it pops all those figures and it has me do them all as if they were positive. Really kind of what it would look like is all of this would pop up and that would pop up, and I'd be finding the area of that. So the absolute value, putting it around the f of x, just means everywhere it went negative, consider it positive. So when I now go from negative 4 to 6, and I have the absolute value, then this would become positive, positive, positive. So I know that that triangle is 1. I know that half the circle is 2 pi, and I already did that triangle as 4. So it'd be 5 plus 2 pi. And the last step, for letter F, what I can do is two things. Really what adding 2 does to a function is it moves it up 2. What it does geometrically is it adds a rectangle onto the bottom, because if you take any function, let's say maybe it looks like that, and if I move it up 2, let's see if I can do that, boom, really it's the same one with a 2 by this rectangle added to it. So what I like to do when I see that plus 2 is I just know that it's going to be the area from negative 4 to 6. Then it's going to add a 2 by 10, because that's how far apart the dx is there. It's going to add a 2 by 10 rectangle to the bottom of whatever it was. So I already did negative 4 to 6 right here, and so I just add 20 to my answer, really. And again, it's kind of important that you understand why that is. It's adding, if you want to even think of it separately, just to show you a little bit more, if you want to break those apart, which is legal, the second one is from negative 4 to 6 of the function 2. And remember, that is a horizontal line at 2. And if you're evaluating it from negative 4 out to 6, you would have a 10 by 2 rectangle being added to that function. So it just adds 20 on. So when you see that plus on the back side of there, it's just adding a big chunk of area to the entire thing. All right, so now let's go combine that with all our properties, and let's head over here to one like, I think I had one on the bottom of this page that I want to look at. I don't know why my screen, I'm looking for moving my screen down here. I'm going to move it up. All right, so let's go take a look at number 6. There's a couple like this in your homework, and they're kind of silly. It looks like a lot of notation, and so let's just pick this apart. What they're doing is they give you one big, long integrand. And you're going to notice that it's a sum and a difference, so you're going to be able to break it apart. You're going to bring constants out front, and then you're going to use these values to complete it. So what you're going to do is you're going to take this, and you're going to split it into the integral from 1 to 3 of x squared with a negative out front, because that's a constant. Then you're going to go from 1 to 3 of 4x dx. And again, constants are coming out front, and I'm breaking apart, so I'm basically using that one and the one above it. And then my last term is just a minus 3 dx, and that actually comes out front. So I pulled all my constants out front, and then I split it up. And now they've given me the values for each one of these. It says the integral from 1 to 3 is 26 thirds. The integral of x dx from 1 to 3 is 4. Whoopsie. Then why did I write a 3? 4. And the integral from 1 to 3 of just dx is 2. And you would just go do the arithmetic for that, which I'm not going to waste video time doing. So last page, let's go use some of these properties, and then that'll be it for notes. I'm trying to keep it at about under 20 minutes. So let's go take a look at what I've got here. They tell me that under the curve from 0 to 3 is 4, and then from 3 to 6 is negative 1. Well, then if I go all the way from 0 to 6, I'll just go from 0 to 3, and then from 3 to 6. So the answer to that would just be 3. It's nice and easy. On letter B, they didn't give me from 6 to 3, but they gave me from 3 to 6. And when I change those limits, I get the opposite of what I would have from 3 to 6. So I'd get the opposite of a negative 1, or just 1. So the properties are pretty easy. This one's by far the easiest, because when you integrate from 3 to 3, no matter what the function is, you get 0, because you won't have any bases on the rectangles, or dx is 0, however you want to think about it. When it has a negative 5, here, constants can come out front. So that'll be negative 5 times the integral from 3 to 6 of the function. And I know what the integral from 3 to 6 is. So I'm going to use what they give me along with my properties to help answer the question. For number 52, we'll just do two of them. We'll do that one. Let's do A and C, just to do a couple. So these are from your book, by the way. So this says, find the possible value of A and B that can make the statement true. If possible, use a graph to support your answer, and you could have more than one right answer. So letter A is going from negative 1 to 1, and then from 1 to 5. Well, I could just go from negative 2 straight on to 5 and do one big region instead of one chopped into two pieces. So for this one, my A would be negative 2 and my B would be 5. What would the graph of that look like? Well, there's a million of them because I don't know what f is. But if I make a fake function, let's just go like this, what this is saying is, instead of doing the area under the curve from negative 2, I got to back up. I can't see what I crossed off here. What was this? Negative 2 to 1. And then going from 1 to 5 and adding them up separately, I could just sweep on through all the way from negative 2 to 5. So that's what that one's saying. For letter C, how would I get the area under the curve of the sine wave? So I need to know what the sine wave looks like. Sine of 0 is 0. Sine of pi is 0. Sine of pi over 2 is 1. So I need to kind of make sure I get this to go like that. And it says, how could I get the sine to be negative, or the area under the curve to be negative? Well, you'll notice that from 0 to pi, this is above the x-axis, so it's positive. From pi to 2 pi, I fall below the x-axis, so my integral would be considered negative. So I could have, and there's other possibilities, but I could have a be pi and b be 2 pi. All right, let's go look at this last one and then be done. So on number 60, It says determine which value best approximates the definite integral. And it says make your selection on the basis of a sketch. So what they want you to understand is that you are approximating the area under the curve. You can't do it exactly yet. That's the next section. But if we know what this graph looks like, maybe we can figure out which one of those would be the best approximation. So let's go graph that. The square root function is that shout out like this, but this one is up 1. So I start at 1, and then let's go. It looks like I'm integrating from 0 to 9. So I'm going to 1, 2, 3, 4, 5, 6, 7, 8, 9. The square root of 9 is 3. 3 plus 1 is 4. So I'm going to kind of end right here. I'm going to do my little shout out like that. It should look a little bit better than that, but I need something that'll estimate the area of under the curve and above the x-axis. Well, this one's pretty obvious because there's two ways to think about it. First of all, even if I just went under this horizontal line, it's a 9 by 1 rectangle. So it's at least, it's not negative because it's above the x-axis. First of all, it's got to be quite a bit more than 9, and it certainly can't be 3 because just this right here is 9. So that's one way to look at it, is just it's got to be the 27. Or you can even do right here, this rectangle right here would be a 9 by 4 rectangle, which is 36, and that's taking up well over half of that. So C has to be your best answer for that. Now, coming up next is not what's the best approximation. Don't draw it. How can I get that exact without touching my calculator? And that's called the fundamental theorem of calculus, and that's going to be one of our next big areas of study. So we are done with this. What you could do if you would like is to maybe, if you have more time tonight than tomorrow, because 4.3 is all going to be due on Thursday, you might want to get a go on some of these so you can ask me if you need help on Wednesday in class. So you might want to continue on with your work. Otherwise, in class tomorrow, we'll have about 10 to 15 minutes more notes, and you'll get a little worksheet. And everything will be due on Thursday. So if you want to kind of space out your homework a little bit, you might want to do this as much as you can tonight so you don't have so much to do tomorrow. Other than that, you have a good one.